Alrighty, so today we are going to be talking about my project for mechanics and materials, which is ME272. And my project is the analysis of the deflection of a fishing. A little bit of background. The application of this analysis is for fishermen who want to know how much their fishing pole is going to bend, as well as knowing maximum weight of fish that their fishing pole can handle. So by bend, or how much it's going to deflect, we're talking about this length right here. And then we're trying to find the maximum load that'll go right here, that will result in this rod snapping. Fishing poles are important to fishermen because reeling fish in on a pole is the common way of catching fish for sport fishing as well as commercial fishing and people that just do it for a hobby. The fishing pole carries the load of the fish from the line that passes through the eyelets and makes its way down to the hook. So in this apparatus here, there's whenever you're fishing, there'll be a reel right here that has line on it. And the line will pass through these eyelets and go all the way down to a hook down here. That's the bottom of the water. And then there will be a fish on it. So there's an applied load right here at the end of the rod that is equivalent to the weight of the fish. And there's also distributed loads throughout the rod at the eyelets because the line is actually touching the eyelets at those points, and that is supporting the line. So you also have to factor that into your analysis. Problem definition. The object I have chose to analyze that is subject to a mechanical load is a fishing pole that is loaded from the weight of the fish. And some requirements for the analysis to simplify things and also to actually be able to analyze something that can give you a number that is pretty reasonable for what you're asking. So the rod is fixed at the handle grip, horizontal and vertical motion. So by that, I'm talking about right here, this is the handle grip. So as you can see, there's these two supports here that prevent both horizontal motion as well as vertical motion. So whenever this is bended, or whenever this is loaded, it bends, and there's a moment that is applied at this point. Actually, technically, it'd be at this point, and so this point up here would have a moment that is equal and opposite to this length axis load. The applied load at the end of the rod is 10 pounds, as we discussed. And there's a distributed load applied at the eyelet of each section. So basically what that means is, like I said, the line touches the eyelet at each of these points right here, at each of these eyelets. So basically what we're going to say is that there's distributed load throughout the rod, and we're going to apply those distributed loads, which would just be a load at each of the eyelets, and the load increments are 3 pounds, 5 pounds, 7 pounds, and 10 pounds. And my fishing rod, we have 4 sections here. So there would be a load of 3 pounds here, 5 pounds here, 7 pounds here, and then 10 pounds at the end. This is not the fishing rod that I am using to analyze. It is just a representation that I found on the internet, and it has more eyelets than my pole does. The diameter of each section is, with respect to section 1, 2, 3, and 4, is 5/8 of an inch, 1/2 an inch, 1/4 of an inch, and 1/8 of an inch. As you can see, the rod is thicker in diameter here than it is at the end. The Young's modulus for a carbon fiber reinforced material that I'm using, or carbon fiber reinforced polymer, is 175 gigapascals. The Poisson's ratio is 0.3. And like I said earlier, the the rod is divided into 4 sections with differing lengths as well as cross-sectional areas due to the different diameters. Design tasks. Most fishermen today use a fishing rod to reel in fish. I am applying a kinematic analysis of the fishing rod under load in order to model how much the rod will deflect, as well as finding the biggest fish that can be caught without snapping the rod. A horizontal fishing rod is fixed at the handle. To prevent horizontal and vertical motion, there are distributed applied loads along the rod that are said to be acting at the location of the eyelets. The pole is divided into 4 sections that have different axial lengths as well as different cross-sectional areas. An analysis is performed to find the deflection in each section of the rod, as well as the total deflection of the rod. The model is assumed to be a cantilever beam type of bending. So basically what I mean by this last 2 sentences is analysis is performed to find the deflection in each section of the rod as well as the total deflection of the rod. So, like I said earlier, we have 4 sections because we have 4 eyelets. And so they all have a certain length and a certain load. So basically what we're doing is we're taking the deflection of this section, which is section 1, the deflection of this section, which is section 2, the deflection of this section, which is section 3, and then the deflection of this section, which is section 4. And so the deflection of section 1 would be about this length. The deflection of section 2 would be from end of that length to here. The deflection of section 3 would be that length to here. And then the deflection of 4 would be that length to here. And then so the total deflection would be just all of these added up. And the model is assumed to be cantilever beam type of bending. And so from that, we are able to use this equation right here, which is the deflection of a cantilever beam under a load that is perpendicular to the beam. And so that deflection is minus P, which is the force, times the length of the axial length of the section cubed divided by 3 times B, and B is equal to Young's modulus times the moment of inertia. So this is the analysis that I did for the dimensions on my fishing pole, and for the first length of the for the section of the first length, I got 24 inches. The force we are assuming is to be 3 pounds at that first eyelet. Young's modulus is just what it is for the carbon fiber reinforced polymer. The radius is due to the diameter divided by 2. Moment of inertia is calculated from the moment of inertia of a circular cross-sectional rod. And we can see that, and then we do all these. We do this for all 4 sections. And as you can see, the eyelets get closer together as you go along the rod. And the deflection of the first section is 0.07 of an inch. The deflection of the second section is 0.15 inches. The third section's deflection is 1.96 inches, and the fourth section deflection is 24.08 inches. So if we add all these up, the total deflection that will result in from the load or the weight of the fish is 26.26 inches, which is a little over 2 feet, which if you're a fisherman, that seems perfectly reasonable for the assumptions that we made. And I haven't quite gotten to figuring out how to calculate the maximum weight of the fish, but that will be in my last